Most people have heard of global climate change. Today, we're concerned with hotter summers, colder winters, stronger storms, and melting polar ice. But what would you picture if someone asked you to think about climate change over millions of years? Some paleontologists take a long view of climate change, reading the fossil record to look back through time to understand how life on Earth responded to the warming and cooling of our planet. Today we'll meet Smithsonian paleontologist Dr. Scott Wing to learn about how a warming event 56 million years ago might help us better understand our changing climate today. Hi, thanks for joining us. I'm Maggie Benson, host of Live from Curious, Smithsonian Science How. We have a really great show for you today, but before we start, I want to ask you a question. You can respond using the poll that appears to the right of your video screen. Has the Earth ever been as warm as it is now? A, for sure, B, no way, or C, don't know. Take a moment to think about it and put your answer in the window to the right. While the results are coming in, we're going to go to our special guest. Today we have with us Dr. Scott Wing, paleobotanist here at the Smithsonian National Museum of Natural History. Thanks for joining us, Scott.
I'm delighted to be here.
So, what does a paleobotanist do?
Well, a paleobotanist is just somebody who studies fossil plants, and fossil plants have been living on this planet for, on the surface of the continents for more than 400 million years. So there's a lot to study. And of course, the planet goes back farther than that, back to 3.6 billion years ago. So.
Wow, so do you study fossil plants for that whole time period, or do you focus in anywhere specifically?
I am very focused right now on a particular period of time about 56 million years ago, when the Earth's climate warmed very rapidly and stayed warm for about 100,000 years.
Interesting. So I see on this map that 56 million years ago wasn't actually that long ago in Earth's history.
Yeah, a lot of people, there's a lot of teasing in paleobotany about, oh, you study those young things, they're only 56 million years ago, but I'm serious, I study things that are much older than that. So yeah, this is 56 million years ago, it's 10 million years after the dinosaurs went extinct. A lot of mammals running around, so it's relatively recent in Earth history, even though it seems like a long time to us.
Interesting. So our results of our poll are in, and our viewers think, 100% of them actually, that the Earth has been this warm before. What do you say?
I say the viewers are right, 100% correct. The Earth has indeed been much warmer in the past. There have been times when there was no ice at the poles. There have been times when there were palm trees growing in Alaska. So it's definitely cool overall now compared to what it has been for much of the history of the planet. But we're also in a glacial age, so it's sort of been going up and down. The last 2 million years, the ice has come, the ice is gone.
And is this what it may have looked like back during that time period?
During the 56 million year ago warm period, we call it the Paleocene-Eocene thermal maximum, lots of words there. We think that it was very warm, and that reconstruction's from Wyoming. And I assure you it doesn't look like a dry tropical forest in Wyoming today.
No, so tell us about this time period, this Paleo-Eocene thermal maximum,
Yeah.
you called it. What is that?
It's a short period, geologically short period, and during that period, starting about 56 million years ago, the climate warmed by something like 5-6 degrees Celsius, which would be 10 degrees Fahrenheit, 11 degrees Fahrenheit, in a period of just a few thousand years. And then it stayed warm for probably about 100,000 to 120,000 years following that. And then it dropped back down to the temperature it had been before that. But of course, this is all during a time period when it's already quite warm. So it's basically a short, really warm interval in the middle of a much longer, also very warm interval.
So we already have a student question. Are you ready to take it?
Sure.
All right. This one comes from Beryl from Arlington. Was the Earth really cold right before that PETM happened?
No, Beryl, it was actually warm even before. So we're talking about a time there are palm trees growing in Wyoming before this event starts. Then it gets much warmer than that, and it gets even hotter, of course, everywhere. So this is a warm period that's inside a longer warm period. It's
Great.
very, very dramatically warm.
Great question. So this PETM, how do scientists have the evidence? I mean, what kind of evidence do they have to know that this actually happened?
Well, the event was first discovered by taking cores in the deep ocean, which is kind of interesting that these white dots you can see on your screen are places all over the world where deep sea drilling vessels have drilled holes in the bottom of the ocean, pulled out sediment cores, and much of the sediment in the deep ocean is composed of the shells of tiny little organisms. These are relatives of amoeba that make a little shell out of limestone, and you can see one of the shells on the screen. And those shells, the chemistry of those shells actually tells us the temperature of the ocean water at the time the shell was made, when the organism was alive. And there are millions of those little shells in the cores.
And that has been looked at globally.
And that's been looked at all over the world now, and we find at this period of time, 56 million years ago, temperatures rose everywhere.
Interesting. So I know that you do work in Wyoming. So what kind of things do you look at in Wyoming to learn about this period of warming 56 million years ago?
Well, because I'm a paleobotanist, I like to look at fossil plants, and one of the reasons I'm interested in fossil plants is because they are very sensitive, plants are very sensitive to climate. So I go out to Wyoming and walk around in the Badlands looking for fossil plants. You can see some of what the Badlands look like here. Very well-exposed rocks. It's easy to see. It's dry today, lots of erosion, so we can see the strata, and we can see the fossils that come weathering out sometimes.
So what makes this location unique for finding fossils?
Well, it's in the Rocky Mountains, and we can use our little tool here, our demonstration device. So during this period of time, between say 66 and 50 million years ago, the Rocky Mountains were bending up, and you can see that as the crust bends and these layers of sediment get raised higher, then these erode off, because these are the tops of the mountains. And the sediment that erodes off there ends up in the basin over here. And so during this time period, sediment was piling up in the Bighorn Basin where I'm working. And in some places, it's thousands of meters thick of sediment that were deposited during this period of time.
And in that sediment, you're finding fossils?
That's the beauty of a place where there's lots of deposition, is that it traps the fossils. So we go around and collect them.
Cool. So we have another student question, and this one comes from Elizabeth. Fort Worth Museum of, this one's from Elizabeth from the Fort Worth Museum of Natural History. How do you measure temperatures from so long ago?
Well, Elizabeth, there are a couple of different ways, and one of them involves the chemistry of those little shells I talked about from the deep ocean. But we also can use leaves to tell us something about temperature. And the feature that's really most helpful has to do just simply with the edge or the margin of the leaf. And I think you can see on some of these leaves, for instance here, this leaf has what I would call a smooth margin, or an entire margin. And this leaf over here has a toothed margin, a jagged margin. And if you go look at forests today, you see that in places where the climate's very warm, that these toothed margins are relatively rare. And if you go to a place where the climate's cold, like Canada, you see lots of species with these toothed margins. So we can actually use the shapes of the leaves themselves to tell us something about the climate.
Yeah, great question. So you go to Bighorn Basin in Wyoming and you look at all of these fossils. But when did people figure out that that was a great place to find them?
I think the first geologist or paleontologist who ever walked into the Bighorn Basin probably thought, that is a place I need to spend a lot of time.
When was that?
That was like 1880, the first scientific expedition to the Bighorn Basin. And so ever since then, paleontologists have been going out there. The first guys were working on horseback, of course, and it took weeks and weeks to get there. But they're doing pretty much the same thing that we're doing. They're wandering around in the Badlands looking for fossils and making very careful notes about what they see. So it may have been a long time ago, but they were very keen observers.
So what kind of modern tools do you have now that give you an advantage over these expeditions 100 years ago?
Well, we have things like GPS devices. So a lot of people have these for hiking, but we use a very similar kind of equipment. That helps us, of course, position ourselves. We also use some somewhat older-fashioned equipment. We use, this is a Brunton compass that we use for determining whether the strata are dipping or whether they're horizontal, and to measure what that dip is.
And when you say strata, that means the actual layers that you're looking at in the rocks.
The layers of rock that are, sometimes they've been pushed up since they were deposited, and so they're not flat anymore, and you need to be able to account for that. We also use maps, old-fashioned maps like this sometimes. We use geology hammers to break open the rocks to find the fossils. And really my favorite is this hand lens. This is a 10-power hand lens. Nothing fancy about it. You can get one very inexpensively online or at a supply store. And this just magnifies the image of the fossil, and you can see much more about it. So it's kind of a mix of tools we use today, both some of them old-fashioned and a lot of them fairly high-tech.
So are there any new discoveries? I mean, if paleontologists have been here for over 100 years, are you finding anything new?
What's new is the questions that we ask. So 100 years ago, people didn't know how to correlate events that were happening in the ocean and events that were happening on land. And so just knowing that, for instance, this period I study, that the climate warmed globally, makes you ask different questions than you would have asked if you didn't know that this was a global event. So we look for different things and we ask different questions than our predecessors did. But we proceed in many of the same ways. We have advantages they didn't have, put it that way.
So you said that the questions are different. What kind of major questions have you had that you've been investigating in Wyoming?
Well, because I knew that this warming period at 56 million years ago happened, I made a sort of prediction that the plants should change very radically. Because if you warm the climate by 5 or 6 degrees Celsius, that should mean a lot to the plants, and that different kinds of plants should show up. So that was my idea that I was trying to gather data to test.
Did you find any plants to represent that period? We're looking at.
Yeah, and here's you can see this period of time represented right in this slide. The stripes that you see are fossil soil horizons. So those are periods during which there was no deposition on the ancient floodplains, and a soil would form and it would oxidize the iron. You get a little red stripe, and then deposition starts up again. So those layers you can actually follow around. That's actually a big help when you're trying to do the geology in the field.
So you actually know how to read those layers.
Yeah, and that's just a matter of going and looking over and over again and making drawings and taking photographs and measuring the rocks. So it's a time-consuming process of getting to know the country in a way. But so there was a long period of time, 11 years or so, when I was looking for fossils from this warming interval and not finding them. And one day in 2005, I think it was the second day of the field season, I was out with my field assistant, a college student who was in the field for the first day ever of his life. And it had gotten kind of late in the afternoon, and it was over 100 degrees, and we were out of water, and we were quite a long ways from the field vehicle. And we went over a hill, and I thought, oh, I just really need to check that place over there. It looks like it might be promising.
Just one more site.
Just one more place. And so I dug in with the shovel, and I saw a fossil, and the first thing I thought was, this is different. This is different from anything I've seen. And so I got on my knees, and I was really digging away as fast as I could, and more fossils were coming out, and I just started to laugh. It made me laugh because I thought, it's exactly what it looks completely different. These are different plants. And I was so happy that my laughter turned into tears. So I was kneeling on the ground in the middle of nowhere, laughing and crying and digging. And then I remembered that I had a field assistant with me, and I thought, oh, he must be really worried. He must think
He wasn't crying.
No, well, if he was crying, it was because he was worried about whether he was going to get back to the car. Anyway, it was a very exciting moment.
It sounds really thrilling.
Yeah, it was.
But those 11 years that you spent looking for these fossils, did you feel like they were wasted in any way?
No, they were actually essential. I'm not sure I would have known what to think if I had found these key fossils before I understood the question. So I went out with the question in mind, and it was because I knew the plants that occurred before the event and after the event that I was able to recognize that they were different. So it's kind of a preparation is how I think of it.
This one comes from Dixon from Altoona. What happens to plants when it gets much warmer?
Well, when it gets warm, a plant can't move. So it either dies or it manages to survive. So the way they do move is through generations, through seeds and dispersal of those seeds. And that's what we think happened during this warming event 56 million years ago, is that it took many generations for plants that were better adapted to the warmer, drier conditions to move into the area of Wyoming that we're studying. And during that time, the populations of plants that didn't do so well died off in that area.
And I understand that some of these collections here today might represent that period of warming.
Yeah, absolutely. We have on this side of the table a bunch of plant fossils that come from the warm period, and over here fossils that come from the cool period before, cooler period, still warm.
How did you tell the difference between them?
Well, a lot of my life involves just trying to sort fossils. So you find leaves, many of them are incomplete, and you have to learn to pay attention to the features that help you distinguish different species. And so a lot of the characters are in the venation of the leaf.
And that's
those are the they show up a little darker in most of these fossils. They're the fine lines, and that's the tissue that carries the water to the leaf and that helps the leaf resist being torn by the wind. And those veins form really intricate patterns that you can see even with just a hand lens, but you can see them better under a low-powered microscope. And they are quite distinctive. So leaves of different species look different in detail when you really zoom in and look at those veins carefully. And then there are also features of the edge of the leaf. Like I mentioned, the smooth leaves and the toothed leaves, those features can be really informative as well.
So you must spend a lot of time sorting your leaves after you go out into the field and collect them all.
That's what I spend much of my winters doing, is just trying to figure out how many kinds I have. It's really one of the simplest ideas in science, is how many kinds of things are here. But it's not very easy to do.
And I know that you've prepared a poll question for our viewers, actually, so that they can test their sorting abilities.
Yeah, this is our Sesame Street. One of these things is not like the other activity.
So perfect. Ready for another poll? It's up on your screen now. Which fossil leaf is not like the others? Take a moment to think about it and put your answer in the window to the right. All right, Scott, can you give us a hint?
Well, the secret with this quiz is not the edge of the leaf, not the margin, but the venation. And it has to do with the major veins in the leaf. So those are the thickest veins, not the fine veins that you might be able to see. And it has to do with how many of those major veins are there.
Right, so we're looking at the veins, the
right, the
structure that carries the water.
Yeah, the structures that carry the water, and they tend to be a little bit darker in these fossils than the rest of the leaf.
So our viewers are thinking that it's C. What does your evidence tell you?
My evidence is that the viewers are correct. It is C. And the reason that it's C is that the leaf C has just one primary vein. So it just has one vein going up the middle of the leaf, and the other two had three major veins, one going up the middle and two from the base going up the sides of the leaf. So that's the difference.
So you spend your time sorting based on these things in exercise like this that you do over and over again.
Right, and I actually, this is not a dead easy one, because leaf C, the one that was different, didn't have the base preserved, so you couldn't see all the way to the bottom of the leaf. And that is the most common problem I have, is that when you're collecting leaves, they don't come out perfect. You know, many of them were broken before they were ever deposited, or you don't collect them quite right and the rock breaks, and so you're missing part, and you still have to see if you can figure out what it is.
Interesting.
Yeah.
So you've spent enough time sorting to know that the ones in the warmer area have smoother leaf edges, the margins. Why did it get warmer during this period 56 million years ago?
Well, the reason why it got warmer is one of the most interesting parts of the story, and the evidence for that comes from the chemistry of carbon. And this is something, again, we can see both in the ocean cores and also in the Bighorn Basin and in other places. There are two kinds of carbon that are stable, carbon-12 and carbon-13. They're called isotopes. And carbon-12 is a little bit lighter, and plants and animals like to use carbon-12 if they can, because it's more reactive. And what we see in both the ocean and on land is a sudden increase in the amount of carbon-12 in rocks and in fossils. And what that tells us is that there was a huge amount of carbon released. In fact, about the same amount of carbon that's contained in modern fossil fuel reservoirs. So thousands of billions of tons of carbon. And that's what changed the climate.
And I see a graph on the screen right now, and this looks like current time. Is that carbon release similar to the carbon release that we're experiencing today?
That's exactly right. So what we're seeing here in the graph is our measurements of carbon made over the last decades. And you can see that it's increasing. Here it is 2006, and it's above 380 parts per million. And this past month, just for the first time, probably in a couple of million years at least, the amount of carbon in the carbon dioxide in the atmosphere was over 400 parts per million. So we're raising the amount of carbon dioxide in the atmosphere, and it's exactly the same thing that happened 56 million years ago, except we're doing it much faster.
Interesting. So we have another student question, and this one comes from Jake. What was the first fossil you discovered?
Jake, I'm not sure I remember the first fossil I discovered. Oh, wait. It was probably a fossil mammal tooth, and it was probably in Wyoming. And it probably wasn't all that far from where I work today, because that was the experience that really got me excited about paleontology. It was right after I graduated from high school. And somebody took me out to Wyoming and said, "You can collect fossils for me." So I did.
So people should go on fossil hunting trips if they get the opportunity.
It is absolutely one of the most amazing things you can do. It's just the joy of discovery is in it, and also the opportunity to walk around in beautiful places.
Absolutely. So I want to get back a little bit to the climate change. The climate change that we're experiencing now, I mean, what have we learned about what's happening now compared to the evidence that you're gathering from 56 million years ago?
Well, the reason that I'm so interested in this warming period 56 million years ago is because it is a lot like what's happening today. The big difference is 56 million years ago, the warming probably took several thousand years. Today, the warming is happening in hundreds of years or even less than that. And so what we're doing is much faster than what was happening then. But the big points that come out of studying this past event are, first of all, if you add a lot of carbon to the atmosphere and ocean system, you get warming. Secondly, that warming doesn't go away. It stays in the system for a long time. So the carbon that was released isn't taken up very quickly. And that's why it stayed warm for 100,000 years during this warming event. And the third thing is it makes the plants and animals have to adjust. So we see these big changes in the flora and in the fauna that go along with the warming.
And we're experiencing that same carbon emission right now.
Yeah, we're seeing many of the same kinds of things, except at a much increased rate, maybe 10 times faster than it happened during this ancient event.
This one comes from Matthew. Besides locating fossils, what is the biggest challenge you face in the field?
Probably the biggest challenge is just getting around, Matthew. It's pretty rough country, and you often end up having to walk a long ways to get where you're going because there's no road that goes there. So also sometimes we get stuck in our field vehicles, and you can spend hours digging yourself out of a mud hole. And there's a fine balance between driving there, which is faster if you don't get stuck, and walking, which is 100% sure to get you there, but can take a lot longer.
This one comes from Jackson. How do you date the plant fossils?
The plant fossils that I find are mostly dated through a process of looking at other fossils that are around them. So you can date rocks by, you can date volcanic rocks that have been heated up by looking at their radiogenic isotopes. So it's basically like they're little clocks in the rock. You have elements that are decaying from one state to another, and you know how fast that happens. And if the rock was heated up, you can use those to tell you the age of the rock. But most rocks are not coming out of volcanoes, so we have to sort of use the fossils to, we have a layer in one place where we actually have a radiometric date, and then we have fossils above and below that, and we find the fossils somewhere else and use the date from over in the other place to tell us the age of the fossil. So it's actually a two-step process.
Wonderful. And can you tell our viewers where they can learn a little bit more about your work?
There's a website at the museum here for the Evolution of Terrestrial Ecosystems program, and you can see the web address on the screen. ETE is the short way to say it, and a lot less of a mouthful. I also recommend realclimate.org. It's a place where climate scientists get on to comment about the latest discoveries that have been made in climate science.
Wonderful. Thank you so much, Scott.
Yeah, been a pleasure.
And thank you so much for tuning in. This show will be archived on curious.si.edu later this evening if you missed part of it. And thank you so much for joining us for our very first season of Smithsonian Science How.